Hello everyone and welcome to the AEE member webinar for Tuesday, March 3rd, 2020. If you are tuning in with us today, you will receive a follow-up email within the next 24 to 48 hours with a link to your certificate of attendance for today's webinar, along with a link to the recording. During the course of the actual presentation, if you have questions for Mr. Eric Oliver, our presenter today, I would be grateful if you could please post those in the question section of your GoToWebinar control panel. We will be addressing questions throughout the course of the webinar. As I mentioned, Mr. Eric Oliver is with us today presenting Chillers 101. Mr. Eric Oliver is the founder of Earthwide LLC, which is an energy and sustainability master planning company in McLean, Virginia. Mr. Oliver is a very passionate energy conservationist. He began his career with the federal government in the EPA's Energy Star Buildings program. He was also responsible for founding EMO, Energy Solutions, in 1998 to address the growing need for energy efficiency services, and he ran that company for 19 years until 2017. With EMO, Eric was among the earliest practitioners of the LEAD program, that's the Leadership in Energy and Environmental Design program, providing energy modeling, commissioning, and lead consulting services in addition to energy auditing capabilities. Mr. Oliver has conducted several dozen energy training seminars, created energy awareness and education campaigns, and has presented and moderated at several energy conferences, including several of our AEE conferences. Mr. Oliver has also worked as a director at 2RW Consultants and was vice president at InScope Innovation. Mr. Oliver holds a master's degree in building technology and a Bachelor of Architecture from MIT. He is a licensed professional engineer in Virginia and Maryland. In addition, he is a former president of the National Capital Chapter and National Secretary of the Association of Energy Engineers. Eric has served on the board of directors of the National Capital Region Chapter of the U.S. Green Buildings Council and is a former board chairman of the Virginia Sustainable Building Network. So without further ado, I will pass control over to Mr. Eric Oliver. Thank you for being with us today and sharing your expertise with our members.
The webinar is going to be a basic introduction into the technology of chillers. And when we talk about chillers in the realm of building HVAC systems, what we're talking about is a mechanical device that generates chilled water for distribution to a building as an alternative to providing cooling at each air handling unit or at each fan coil unit. What chillers allow designers and building operators to do is have one single device that generates chilled water that can then be distributed throughout the building, where it can pass through air handlers, fan coil units, and other devices to provide local cooling. It saves both energy and it also saves design and installation costs. So we're going to be talking about different types of chillers and then how chillers can be used to save energy in buildings. When we talk about chillers, chillers fall into essentially two primary categories, air-cooled chillers and water-cooled chillers. Air-cooled chillers, every part of the chilled water system is packaged in one unit, which is located outside the building. And with a water-cooled system, a water-cooled chiller needs to be paired with a cooling tower, which is a separate device that's typically located outside of the building. So chillers, just like any other cooling device, the basic insides of the chiller system was called the vapor compression cycle. So I'm going to talk a little bit about what that is. How do we cool water down using electricity or other sources as an input? So these are the four basic parts of the vapor compression cycle. You have an evaporator, which is where warm, chilled water returns from the building and then gets cooled down to provide cold, chilled water, which then gets distributed out to the building. You have a compressor, and the compressor is where the energy for the chiller goes into the system, and it's used to compress the refrigerant. Then you have a condenser. The condenser is where energy is removed from this closed refrigerant loop, and then an expansion valve is where a warm liquid refrigerant gets expanded, and what comes out of the expansion valve is cold refrigerant that's then used for the evaporator. So these are the four basic components of a vapor compression cycle, and whether it's a heat pump or whether it's a chiller or any other type of cooling device, this is the basic technology that drives it. Now, how does this work and why was this invented? So we'll take a look at it on a part-by-part basis. So what you have is, let's start with the very beginning, which is what we need inside the chiller, which is cold refrigerant liquid. So you have a cold refrigerant liquid in the chiller that passes through an evaporator, and that cools down the warm return chilled water. So chilled water gets supplied out to the building, typically around 45 degrees, passes through the air handling units and fan coil units, gets warmed up by cooling down the air, and then returns back to the evaporator where it passes over the cold refrigerant liquid and cools down again to complete its cycle in the building. So that cold refrigerant then becomes a warm refrigerant gas. So the question is how do we get that warm refrigerant gas back down to a cold refrigerant liquid? And you can't cool it down just by blowing air over it. Typically, these are run in the summer where the outside air is warm. So how do we get this warm refrigerant gas back to a cold refrigerant liquid? And the way we do it is by something that is based on the ideal gas law, which is what you see in the upper right there, PV equals nRT, which basically tells us that pressure times volume in any closed system is equal to a constant times temperature. So if you divide by temperature, essentially what you're saying is that the pressure and volume divided by temperature in any point in that refrigerant liquid is constant. So if you can compress a liquid or a gas inside a loop, you increase its temperature and pressure. And if you expand that, therefore increasing its volume, you decrease its temperature and pressure. So if we were to take that warm refrigerant, compress it, then all of a sudden it would be at a very high temperature and pressure, and that would be a way that we could then remove energy from it before expanding it and getting back to that cold refrigerant liquid. So after the warm refrigerant gas passes through the compressor, and we'll talk about the different types of compressors, but energy goes into powering a compressor, which is a device that presses that down that liquid, reducing its volume, increasing its pressure and temperature. And then what comes out of that compressor is what we call a superheated pressurized refrigerant, very hot, very pressurized. And now that's something that we can remove heat from. So that refrigerant then passes through the condenser. In water-cooled chillers, that's a device that's connected to the cooling tower. In air-cooled chillers, you have warm outside air directly blowing over it. So you have air blowing over that superheated pressurized refrigerant, you're removing energy from it, and then what comes out of that condenser is now just a warm but still pressurized refrigerant liquid. So then that warm pressurized refrigerant liquid passes through what's called an expansion valve, where it's the opposite of the compressor. So where the compressor compresses the refrigerant and increases its pressure and temperature, the expansion valve opens that refrigerant back up, then decreasing its pressure and temperature. And because we've already removed energy from this refrigerant loop at the condenser, now we're back to our cold refrigerant liquid, which can then cool down the warm return chilled water, and then the whole system repeats. So this compressor cycle, this it's called the vapor compression cycle. By compressing the refrigerant, you can then remove energy from it. By expanding it, you get it back down to cold refrigerant. This is how every refrigeration system works in the world, and every mechanical at least, refrigerant system works in the world. So this is, when you look at the insides of a water-cooled chiller, this is what it looks like. If you see a water-cooled chiller in the mechanical room without the breaks in the tubes, this is what it looks like. So the evaporator has many, many tubes in it. And this is where the refrigerant loop, the closed refrigerant loop, exchanges heat with the return water from the building. So you see the two pipes on the lower left, that represents the water that returns from the building, passes over the tubes in the evaporator, goes back out the other side where it gets pumped back out to the building. And all of those tubes contain refrigerant, which is powered by the compressor. The compressor, when you see the large enclosure above a chiller, that houses the compressor. And we'll talk a little bit about the different compressor types, but that's what compresses the refrigerant, then passes it through the condenser. The condenser is the other tube that you would see in a chiller in a mechanical room. And each of those tubes on the top represent water coming from the cooling tower, passing over the superheated refrigerant, cooling it down, and then going back out to the cooling tower. And the box on the right is the control panel, typical for a chiller, controls this whole process. And so when you look at a water-cooled chiller, this is what it would look like, but these are the three basic components. You have the evaporator, you have the compressor, and then you have the condenser. With an air-cooled chiller, everything is in one package. So you don't have a cooling tower that's separate from the water-cooled chillers. So what you see on the left is typically what it would look like. If you see an air-cooled chiller outside of a building they're typically located either on the ground or on a rooftop. You still have the inlet for cooling water. So you have water coming in from the building that's been warmed by the air handling units and by the fan coil units, passes over the refrigerant where it gets cooled down in the evaporator and then goes back out to the building. But instead of having a separate distribution system to a cooling tower, this refrigerant goes up into the condenser section of the air-cooled chiller where outside air is blown directly over this superheated refrigerant. And even if the outside air temperature is 90 or 100 degrees, the superheated refrigerant is much higher temperature and pressure than that. So blowing air over the refrigerant directly will still remove enough energy from that refrigerant so that when it goes back down into the expansion valve, it gets expanded out at the lower half of this chiller. It'll then generate your chilled refrigerant, which can then be used to cool the building water. And then all air-cooled chillers have fans on the top, which are used to draw air across the cooling coils on each side of the top and cool down the refrigerant. So air-cooled chillers are typically all in one package, not as energy efficient as water-cooled chillers. Water-cooled chillers, even when you factor in the cooling tower, use much less energy for a given cooling load than air-cooled chillers do. They're also more expensive, but that's the trade-off, is that you spend a little more to use water-cooled chillers than you would if you used an air-cooled chiller. But there may be situations in a design where you don't have room for a chiller in a cooling tower, so you may design in air-cooled chillers instead. So there's a variety of reasons why you would pick one over the other, but those are the two basic types of chillers that are out there. Now, when you talk about the different types of water-cooled compressors, you'll hear terms like a centrifugal chiller or a scroll chiller or a screw chiller or reciprocating chiller. And what that defines is the different types of compressors. All aspects of a water-cooled chiller are the same across the different models except for how you compress that refrigerant and how it's mechanically done. So we'll go through what each of those types actually mean in terms of the physical attributions of it. So reciprocating chiller, these were the first types of chillers that were manufactured, and it operates like a piston. So you have a chamber where the refrigerant gets pulled in through one valve. You'll see in the upper section there, refrigerant gets pulled in, what they call the suction part of the refrigerant compressor, through section 1 into the chamber, which is section 3, and then the piston compresses that refrigerant and then sends it out through the valve in section 2. So it's drawing refrigerant in through the left, compressing it in the chamber, and pushing it out the other side. It's a very, very simple, very basic piston-based method of compressing the refrigerant. In a centrifugal compressor, which is what you see on the bottom there, the suction line, which is also called the inlet pipe, draws refrigerant in through the center of a wheel and with inverted blades. And so that wheel spins around with electrical energy. The impeller compresses the refrigerant against the inside of the pipe, and then presses it out through the outlet pipe, the discharge. So it draws suction refrigerant in, compresses it, and then pushes it out the outlet pipe. Centrifugals are slightly more energy efficient than reciprocating compressors in terms of the amount of energy input you need. Screw and scroll chillers are the most modern type of compressors and also the most energy efficient. With a screw type chiller, you have a series of gears where the suction side of the refrigerant draws refrigerant into and in between the gears and screws of this chamber, and in between the screws and the gear compresses the refrigerant and then discharges it out the other side. So it's another method of drawing refrigerant in, compressing it, and then sending it out the other side. And with a scroll chiller, which is in generally the most energy efficient type of chiller, you have two concentric scrolls. The one that you see in black here represents a fixed scroll, and then the one that you see in gray represents a rotating scroll. So it rotates, the one rotating scroll rotates inside the fixed scroll. So the refrigerant is drawn in through the outside. It is compressed by the rotating action of the scroll until it reaches the center of the scroll, and then it gets discharged out through that side. So it's another method of drawing refrigerant in, compressing it to a certain pressure and temperature, and then discharging it out. So when you hear about different chiller types, scroll, reciprocating, centrifugal, that's all that means. That means that these are the different types of compressors that are used in that system. Now, the newest type of chiller that has come out, the most recent technology, some of you may have heard, is called maglev, or magnetic frictionless chiller. It's essentially a centrifugal chiller, but the shaft that rotates the compressor is held in place not by bearings and gears, but by magnetic levitation. And so that removes a significant amount of friction inside the unit, which greatly reduces the amount of energy that you need to run that centrifugal compressor. So these are with a combination of frictionless bearings, permanent magnetic motor, inverter speed control, and a centrifugal compressor. You can generate the same amount of cooling load with much less energy that goes in, and we'll talk about how much less a little bit later on. But this is, you know, like everything else, this is probably the most expensive type of chiller in terms of cost per ton, but it's also by far the most energy efficient. So there are trade-offs you need to make when deciding what kind of chiller you would use for a system. So when you talk about the metrics of chiller energy efficiency, these are the basic terms that you'll hear out there. These are the different metrics they use. The one that you'll hear most often is kW per ton, and that's kilowatts of electricity input into the chiller per ton of cooling output. And a ton of cooling refrigeration is defined as 12,000 BTUs per hour. So when you decide how many BTUs per hour of cooling that you need, that's one refrigeration ton of cooling. The amount of kW that goes in per ton of cooling is your kW per ton. And as you can imagine, the lower the kW per ton, the more energy efficient a system is. And so when you look at the variety of water and air-cooled chillers out there, the kW per ton typically falls in the range of 0.3 to 1.2 kW per ton. The next metric you'll hear used a lot is what's called IPLV, or integrated part load value. And what this does is this recognizes that when you hear about a kW per ton of chiller, that's the kW per ton operating at full load, 100% load. But the kW per ton of a chiller varies based on part load. The bottom is a representative of a chart where the x-axis is the percentage load from 0% or 20% up to 100%, and the y-axis is kW per ton. So for any chiller, every chiller has its own performance curve, but the performance varies based on the load of the system. So it's not just, if you buy a 1.1 kW per ton chiller, that just means how many kW per ton it uses at peak load, and it varies. So the IPLV, what it does is it takes an average of the rating of that chiller at 25%, 50%, 75%, and 100% load, takes the average of that and then gives you more of an idea about how that chiller is going to operate, because chillers operate 99% of the time at less than 100% load. So this is more accurate if you're trying to figure out how much energy a chiller is going to use, is using the integrated part load value. Another metric is coefficient of performance, or COP. This is more commonly used with small heat pumps, but can be used to define chillers, and it's essentially the BTU output divided by the BTU hours input divided by the BTU hours input. So, so the higher the coefficient of performance, the more work you get out of a specific energy input. So it's kind of the opposite of kW per ton, and that the higher COP are the more efficient chillers and heat pumps and other types of cooling units. And then energy efficiency ratio is just essentially that same COP, but it's watts per BTU hour instead of BTU hours per BTU hour. So it tells you the amount of energy input in watts for each BTU of hour of cooling it provides. And you'll typically see those in the range of 9 to 24 in terms of EER. You also see a term SEER, which is seasonal energy efficiency ratio. Most commonly, those are used with heat pumps and small compressors, but what that means is that recognizing that that equipment operates different in the winter than it does in the summer, and different outside air temperatures, it takes into account weather impacts on how efficient a system operates in terms of the energy input for the energy output. So these are the metrics that you'll typically see when you're looking at the energy efficiency of chillers and comparing them against each other. So I mentioned that some chillers are more efficient than others. This is a typical curve for the different types of compressors that we talked about before. Most chillers have a cutoff at 20% load, meaning they will operate at lower than 20% load. So between 20 and 100% load, you'll see the curves typically with reciprocating chillers and screw chillers and centrifugal chillers, the efficiency or the kW per ton of the chiller drops from 100% down to 50%, and then climbs back up as you get down to lower loads of 20%. And what this shows you is that most chillers operate more efficiently at 50% load than at any other part in the point load curve, and that's pretty typical in everything except the maglev chillers, and that's going to be important in some of the slides that we talk about later in terms of how to reduce energy consumption of a chiller system. But with the maglev chiller, because of the variable speed compressors and because of the frictionless shaft and because of other inverter impacts, the kW per ton drops pretty dramatically through part load conditions. So, so when you look at the peak kW per ton of a maglev chiller, the input drops pretty precipitously as you reduce the load on that chiller. So that's why they are much, much more efficient than other chiller types.
Eric, we have one
Yes.
question. I'm not sure if this is a good
Sure.
time to address this one or not. You can tell me if you want to address this now or wait. It says, could
Sure.
you please briefly explain the concept of VRF refrigeration in terms of the operation of the chiller and the control of the refrigerant flow?
Yeah, VRF systems don't use chillers. They use a condenser, which is located outside the building. But VRF stands for variable refrigerant flow, also referred to as VRV, or variable refrigerant volume. And in those type of systems, you don't have chilled water at all. You just have refrigerant. And then the refrigerant flows to different diffusers in the building, back to a condenser. And then the condenser is used specifically to remove or add heat to the refrigerant loop, and the refrigerant flows directly in between diffusers in the spaces. So with a VRF or VRV system, there is no chilled water. It's just the closed loop refrigerant that's sent throughout the building and is used to heat and cool spaces. One of the benefits of a VRF system is that any diffuser in the building can be either in cooling load or heating load. The system doesn't have a cooling or heating mode. Any of the diffusers can be either cooling or heating, depending on what the space needs, because it uses the refrigerant directly and adds or removes heat from it. So it can be very efficient in certain building types, but it's different than a chiller in that it doesn't involve any chilled water.
Thank you.
Sure. So when you look at a typical chiller system that involves both a chiller and a cooling tower, this is essentially what you'll see. So in terms of design conditions, you'll have your chiller, and the chiller will pump water throughout the building, bring it back at a higher temperature, and then that the heat that's removed from that chilled water gets dumped into the condenser, where the condenser water, then the heated condenser water, so you can see the temperature, the green temperature above the word compressor. Typically that cooling tower water comes out at about 95 degrees, gets pumped over to the cooling tower, where it's sprayed down into the cooling tower, air blows over it and up through the top center there, and by air blowing over that water directly, it cools it down. So in a you'll typically design a system like this to take 95-degree cooling tower water, cool it down to about 85, where it goes back into the condenser and then picks up heat from the superheated refrigerant again. With the evaporator, you'll have chilled water being discharged into the building. This sheet mentions 40 degrees. It could be 40, 45, 47, 50, and then it typically comes back at 10 degrees warmer than that. So you design a chilled water system for what we call 10-degree delta T. So the difference between the chilled water return and supply is 10 degrees, and the difference between the condenser water to the cooling tower and back is 10 degrees. Now it operates at different temperatures based on the part load, but it's typically when you design a system, you design the capacities to meet 10-degree temperature difference, both on the chilled water side and on the condenser water side. And this is what we call the chiller system. It includes the chiller, the cooling tower, and the distribution pumps. So I want to see if there are any more questions about how chillers work and what the different types are. Now we're going to enter the part of the conversation that deals with, so now that we have different chiller systems and types, how do we reduce energy consumption of a chilled water system? Are there any other questions before we jump to here?
Let's see. First of all, somebody is asking, will the presentation be provided to participants? If you missed the introduction, let me just say that I will be providing a follow-up email in the next 24 to 48 hours with a link to today's recording, but also you'll have the information in there to be able to reach out to Mr. Oliver directly with any follow-up questions and to request copies of the presentation. Next question is, do you by any chance have some kind of pointer so that when you are referring to a part of the equipment or a curve on a graph, you can actually show them exactly the part you're talking about?
Yes, that's a good question. On my laser, obviously my laser pointer wouldn't work, but is this
that would work great.
Yeah. Okay, great. Yeah, thanks. I wish I had earlier. Okay.
The next question is, what is the advantage of a water-cooled chiller?
Water-cooled chillers, they come in two advantages. One is they come in bigger sizes than air-cooled chillers. So if you have a larger system, there's some air-cooled chillers just don't come in larger sizes. And the other advantage is that it uses less energy. So chilled water systems use less energy than air-cooled chillers. Good question.
Okay. Next question is, what is the temperature of delta 10 degrees? What happens if it becomes more or less than that?
If it becomes less than that, there's no problem. If it becomes more than that, if you're sending water out to the building and it comes back 15 or 20 degrees higher, the chiller that you've designed might not have the capacity to cool it down to what you need it to. So if the chiller is designed to provide a 10-degree temperature drop, and the water comes back hotter than 10 degrees above the supply temperature, what's going to happen is that the chilled water supply temperature is going to climb. It's going to go above 45. It may hit 48, 49, and then there may be some air handling units that might not be able to cool down the air enough. So it might sacrifice the ability of that chiller to cool down the whole building.
Okay, let's see.
Great.
You've got several questions right now, so we'll address a few and then we may move on and get to the rest at the end. So please be patient if we don't get to your question right now. What is the minimum chiller capacity for a water-cooled system? Any suggestions?
From what I've seen, it used to be 50 tons. They have 30-ton water-cooled chillers, but nothing below 30 tons and very few below 50 tons. So usually see the smallest water-cooled chiller you'll see is about 50 tons. And the largest air-cooled chiller you'll see is probably 150 to 200 tons.
Okay, great, thank you. How do we choose to go for a screw, scroll, or centrifugal chillers?
Just like anything else. You have a trade-off between a higher cost versus more energy savings. So what I would recommend, the best thing to do is, if you're considering different types, is to do even a quick energy modeling exercise where you try and simulate the energy savings of different chiller types based on the part load curves, and then compare your future energy savings to the additional costs, and then decide which is best for you. Of course, I would always recommend the most energy efficient chiller, but I know every project has a budget, and so it's up to you to compare the two, the additional costs versus the additional energy savings.
Okay, we've got some of them are follow-up to previous questions, so I'm actually going to pause on the questions right there and let you continue with the presentation.
Yeah, and we'll leave some time for follow-ups and questions at the end.
Okay.
Great. So now we're going to talk about, if you have chiller systems, how to save energy, how to reduce the energy consumption of a chiller system. And these are some of the strategies that we're going to talk about in the next few slides. Some of them you may have heard of before: variable speed compressors, variable speed pumps, which are controlled by variable speed drives. The condenser water temperature, we've mentioned that it typically is designed to come back to the chiller at 80 degrees, how lowering that temperature can save energy. How you control the different chilled water and condenser water temperatures can save energy. Modular chiller design, the option between, because we're taking advantage of 50% usage during part load curves, how maybe looking at 2 or 3 smaller chillers versus 1 larger chiller, and then something called waterside economizer, which I'll explain a little bit more. Some of you may have heard that term before. So some of you may have seen this, variable speed compressors, variable speed pumps. A lot of chillers now have the option of being provided with variable speed compressors, and that's an add-on typically to a chiller, but very significant impact on energy consumption. And then the pumps, both the pumps that provide chilled water to the building and that provide condenser water to the cooling tower, can be retrofitted with a variable frequency drive. And so the power that goes through a variable speed drive to power a motor is proportional to the speed of the flow cubed. And so what that means is that if you look at the peak power through to a motor at 100% speed, if it's controlled with a VFD, the percentage of power input is equal to the percentage of speed cubed. And so when you look at the chart there, the green line represents power input, which is the y-axis, versus flow rate if you power a motor using a variable frequency drive. So as you can see, starting with 100% power at 100% speed, the input power drops very quickly, and that curve represents a cube curve, so that if you are at 50% flow rate, you're not at 50% energy input, you're at 50% times 50% times 50%, which is 12.5% input kW. So with the variable frequency drive, and this is true in any application, whether it's a supply fan or a pump or any kind of motor, the power goes down pretty significantly. That's 87.5% energy reduction for a 50% reduction in flow. So, putting variable frequency drives on the pumps or buying a chiller with variable speed compressors reduces power input pretty significantly. I mentioned condenser water reset. So with most chillers, and this is a function of the chiller that is different based on models and manufacturers, but one truth is that if you take that 80-degree temperature that's typically designed to go into the condenser section of the chiller, if you can drop that temperature down to 75 or to 70 or to 65 degrees, by having a cooler condenser water temperature go into the chiller, it operates at a much lower kW per ton. And this is true of most chiller types. This is an example of 4 curves for 2 different types of chillers at 100% load. Doesn't matter what load it's at. If you had an 80 degrees, so these are the x-axis goes from 85 degrees entering condenser water temperature all the way down to 59. And you can see that as the condenser water temperature drops at 80 degrees, it looks like it's around 0.475 kW per ton. If you can drop that all the way down to 65 degrees, now you're down around 0.3 kW per ton. So if you can design or operate a cooling tower so that it doesn't just return water to the chiller at 80 degrees, but can drop that temperature pretty significantly, then you can reduce overall energy consumption of your chilled water system. And this is something I see a lot of times that I discourage is you'll have building owners that will put variable frequency drives on the cooling tower fans to modulate cooling tower fan power to hold that condenser water at 80 degrees. And I tell them, don't do that. Let those fans operate full bore, because if you can run those fans higher under drier and cooler outside air conditions, you can get that condenser water down much, much lower, and the chiller then uses much, much less energy. So you might use a little more energy on the cooling tower fans, but much less energy on the chiller. And so the overall system uses a lot less energy. It's a strategy called condenser water reset, or floating condenser water temperature. Chiller optimization by taking advantage of these part load curves. Now the way, if you have a 2 chiller system, even if they're exactly the same chiller with the exact same part load curves, the way they typically work is what the table on the left you see there. So as the cooling load on the building goes up, you have one chiller that ramps up its operation up to 50% and 100%, and then when chiller 1 is operating at 100% at full load, then the second chiller kicks on. And the chiller number 1 stays at 100%, chiller number 2 ramps up its output until you get to 100% load when both chillers are operating at 100%. But what you're doing there is you're not taking advantage of the part load curves. What you see in the same curve, the system kW per ton, at each part in that, at 25% is 0.65, at 50% with one chiller at full load, which is its highest kW per ton, it's at 0.75, and then you're up around 0.71. What a better strategy is, if you have 2 chillers, as you see in the table on the right, is you start both chillers at the same time at 25% load each, and then you ramp both of them up together. So what you're doing is you're operating more of the year, more times, more of the part load around that 50%, which is the lowest part of that kW per ton curve. So that even if you factor in all of these bins, you're operating at a lower overall kW per ton because you're taking advantage of the chillers operating at part load conditions, which are more efficient than at full load. So this is called chiller optimization. And if you have 2 or 3 different types of chillers with different part load curves, it becomes a little more complex. But what you're doing is you're taking advantage of the part load curves of all of the chillers and running them at different percentages to reduce your overall operating kW per ton. Modular chiller design. So I kind of briefly mentioned this before, is that when you're designing a building or designing a replacement of a chiller system, say you have even the same chiller with the same chiller curve. If it's operating at 150 tons, say you have a new 200-ton chiller, so that's operating at about 75%. That's going to be running at about 0.6 kW per ton. An option is then choosing 3 or 2 smaller chillers and operating more chillers at that part load. So if you have the same 150 tons, where you have 1 chiller operating at 75%, or 3 smaller chillers operating at 50%, now you're right at that sweet point in the kW per ton curve, where you're at 0.48 kW per ton. So for the exact same cooling load, if you have 1 chiller, 1 bigger chiller that consumes 90 kW, you could have 3 smaller chillers operating at 72 kW. There are other advantages to a modular chiller design. For example, if 1 chiller goes down, you still have 200 tons of capacity, so you can still provide the building, or you can rotate them, or you can pull one off for maintenance. There are other benefits to that, but one primary benefit is it really helps with your chiller optimization. You can take advantage of the lower points of that curve, even for the exact same chiller or chiller type and the same chiller part load curve. Now, this is what I mentioned. Some of you may have heard the term waterside economizer before, but essentially what that means is that you have this chiller system and you have the cooling tower, and the system is designed so that the chiller provides the chilled water for the building. Say it's at 45 degrees. And then the condenser water goes up to the cooling tower, is cooled down, and then comes back at 80 degrees. I mentioned before that you can drive those fans on the cooling tower more to get that condenser water temperature down lower. There are certain outside air conditions, and this happens more often than you would think, where say you have 65 degrees outside, but the wet bulb temperature is 35 degrees. Say it's relatively cool but very dry out. If you drive those cooling tower fans, you can get that water down to 42 degrees coming out of the cooling tower. And then you can use that to provide the chilled water for your building and shut the chiller down completely. So there are many times in the year, particularly during dry climates, and when you need to run the chiller for chilled water when it's 65 or 70 or 55 degrees out, where you can use the water coming out of that cooling tower to provide that 45-degree water for the building. So the water comes out at 45, the chiller's shut off, it just passes through it, goes out to the building, comes back at 55, and then that 42-degree condenser water, through its separate heat exchanger, can then cool that water back down to 45 degrees. So if you have a typical say 200-ton chiller, even if it's operating at 0.6 kW per ton, that's about 120 kW of electricity being used for that chiller. And if you have, say, 3 cooling tower fans that are 15 horsepower each, operating about 10 kW, that's 30 kW. So you've gone from 120 kW to provide that 45-degree chill water down to 30 kW. So a very significant electricity reduction. And it's an added cost. You have to add the cost of putting that heat exchanger in, and then you need controllers to recognize when the outside air is cool and dry enough that you can use just the cooling tower alone to generate that cold water. But you actually see this quite a bit out there in terms of energy saving measure. So that's actually it in terms of describing chiller systems and energy saving strategies. And we do have a bit of time, so I'll open it back up to questions.
Okay, so we do actually have several questions and comments. Some of these refer back to previous questions, and I don't have those in front of me anymore, so please forgive me if this doesn't flow very well. But
sure.
Someone said, I mean, does it use less energy? What is the thermodynamic advantage? But I can't remember what that's in reference to, so I apologize on that one. One is, what is the lift in the chillers and what benefit and efficiency?
Well, yeah, chillers have different lifts, different designs. So there's no one answer for that. You know, chillers are designed to you know, provide a 10-degree delta T on the chilled water side and on the condenser side, but there's a variety of different manufacturers and different models will have different characteristics.
Okay, so the question before was, what is the advantage of a water-cooled chiller? For example, he means, why does it use less energy? What is the thermodynamic advantage?
So the one of the main reasons that it uses less energy is because if you have an air-cooled chiller that is that requires outside air to cool down the refrigerant, at most times in the summer that's pretty hot, 90 degrees, 92 degrees, 95 degrees. So you have to compress, you have to spend more energy compressing the refrigerant up to a higher temperature to allow 90, 95 degree hot outside air to cool that down. Whereas if you have a water-cooled chiller and the water in the condenser is at 80 degrees, you don't have to compress that refrigerant to as high a pressure and temperature to allow it to be cooled down by 80-degree water. It's also the same reason why, for example, geothermal heat pumps use less energy, because the underground temperature of the earth is pretty constant at 60 degrees. So if you're discharging heat to the ground at 60 degrees, you don't have to compress that refrigerant up to as high a temperature and pressure to cool it down with 60 degrees as you do with 80 degrees. And with an 80-degree condenser water, it's less energy than, you know, having to compress it high enough to be able to be cooled down with 90, 95, 100 degree outside air.
Okay. This question, the low delta T syndrome may also cause low energy performance of the chiller. That's a question.
Yes, so that's a good point. That's a good point. So you can't, if the delta T gets too high, then you might not be able to meet the chilled water supply temperature. But if the chilled water delta T gets too low, then you're going to have operating problems with the chiller. It can't handle a low delta T, which is why most chillers have minimum load of 20 or 25%. So it'll only operate at 20 or 25% or higher. It won't operate at lower. And what that essentially means is a 2 or 3 degree delta T. That's about as low as they'll go before they start to have problems.
Okay. For air-cooled condensers, which are rated considering 35°C air temperature, how can we compare the kilowatt per ton in winter or hard summer with the design? Kilowatt TR, which is done at 35 degrees C? Question mark.
35 degrees C. Okay, so that's pretty hot. I can't do the math in my head, but you know, when chillers are rated by the manufacturer in terms of peak kW per ton, they're typically rated based on ASHRAE 1% design conditions, which is actually different by location. They're typically in the range of, you know, 92 degrees, 40% humidity, but when a manufacturer rates its kW per ton, I don't know exactly what design parameters they use. They typically use ASHRAE 1%, but you're all right, is that it will operate differently under different, you know, 35°C is going to be pretty high, so that will you won't necessarily be able to use that manufacturer's rated kW per ton. That's a good point.
Okay, you may have already addressed this one, but I'm going to go ahead and read it. You mentioned that less than 10 degrees delta T isn't an issue, but do you have any suggestions for dealing with low delta T syndrome?
Yes, and that so as I mentioned, most chillers cannot handle anything lower than a 2 or 3 degree delta T, and so one way to deal with that is to reduce the flow rate through the chillers. So if you put a variable frequency drive on the chilled water loop, one of the ways that variable frequency drive can be controlled is if it recognizes that the delta T is getting too small, it'll slow down the flow of water through the chiller. And so by slowing down the flow of water, the delta T starts climbing up. So you want to be in that sweet spot of 5 to 10 degrees, and that's one way to do it, is by reducing the flow rate through the chiller.
Okay, for modular chillers, is it better to have 2 chillers running at 50% or 1 chiller running at 100% to cover this load?
It's always better to have 2 chillers at 50%. That's the sweet spot in the part load curve where it's at its lowest kW per ton. And so you want to be around that as much as possible with whether it's 2 chillers or 3 chillers or 4 chillers, whether they're different sizes. When you design the algorithm that decides which chillers come on and when, you always want the chillers operating as close as possible to that 50% load.
Okay. What is the cost comparison for 1 versus 3 chillers?
It depends on what type of chiller it is. And so if you're talking about the same capacity, if you're talking about 1 300-ton chiller or 3 100-ton chillers, the prices are going to be pretty much the same. If it's the same type of chiller, same manufacturer, same model, it's going to be pretty close. But one of the things that designing 3 chillers allows you to do is build in redundancy. So you may be looking at an alternate between 1 200-ton chiller or 3 100-ton chillers, where you're spending more for the 300-ton chillers, but you're building in some redundancy that will protect you in case a chiller goes down. So if you're talking about the same total capacity, it's going to be about the same price. The 3 chillers will be a little bit more. But if you're looking to design in redundancy, you'll be spending a little bit more, but it'll be beneficial in the long run.
Okay. Says, although you can reduce power significantly with pump speed reduction, isn't the pressure impacted as well?
I assume you mean the pressure within the chilled water loop. And yes, so as long as you're operating within the ideal pressure parameters, where we're getting enough pressure to the farthest air handling unit or fan coil unit in the chilled water loop, as long as you're operating within those correct pressure parameters, then it will save you energy. So in other words, you can't use the VFD to drop flow down to 2%, because that won't give you enough pressure for the building. You have to decide to figure out at what point you cannot drop the VFD span below speed below and still provide chilled water to the whole building. So yes, you have to be within certain pressure parameters so that you're meeting the building cooling needs. But anything below 100% with a VFD is going to save a lot of energy.
Okay, what is a good rule of thumb for setting the condensing water temperature? Is faster fan speed always better?
I think so. Some people may disagree with me on this, but I think so. So I always think that the lower you can get the condenser temperature, the more energy you're going to save altogether when you're looking at the whole system. As I mentioned before, if you increase the speed of 3 cooling tower fans, and therefore you're adding maybe 10 to 15 kW, and you can drop that condenser loop temperature down to 65, for example, you might save 100 kW on the chiller and spend an extra 20 kW on the fans. So I think it is always more beneficial to run the cooling tower fans more, get that condenser water temperature down, because almost all chillers operate at a much better kW per ton at a lower condenser temperature.
Okay. Let me see. Could you comment on different waterside CHW loop and how to pick them?
Not sure I understand that question.
No, I read the question as it was stated. So let me just see. So whoever typed that question, if you wouldn't mind rephrasing that, we can try and address that. Is water consumption a concern in the design of water-cooled systems?
That's a great question, and yes, it is. So whenever you have a cooling tower and you have the condenser water that flows to the top and sprayed down, and that water gets cooled down, you're going to have evaporation. And so every condenser loop in a cooling tower system has makeup water that you need to bring in. And so, yes, that is definitely a concern, is that you need makeup water whenever you have evaporation out of a cooling tower. Now, one kind of unique solution I remember seeing once for that was there was a laboratory down in Houston, Texas, where the weather is very humid. And so when air blew over the cooling coils in these large air handling units, you had water condense out and go into a condenser pan and then drain out. Well, they were able to capture that water that condensed out of the air and use that for makeup water for the cooling tower. It's a very unique solution. It wasn't able to provide 100% of the makeup water for the cooling tower, but a big portion of it. And so by capturing condenser drain pan water from large air handling units and using that to feed the cooling tower, they were able to mitigate some of the water losses. So yes, that is a concern with cooling tower systems, is evaporation, but there are ways to address it.
Okay, what are some easy strategies to avoid chiller surge with an oversized system?
That's a good question. I mean, if the system is significantly oversized, there's not a lot you can do. You can install bypass valves and bypass loops in the chilled water supply system, so that some of you're generating more flow than the building needs, but some of that flow is returning back to the chiller, and that may mitigate some of those issues. But really, for a significantly oversized system, that may be, you'd be looking at a good opportunity for putting in new modular chillers.
Okay. Can you please explain how I can calculate the savings for my chiller when I have an upgrade? How does the refrigerant type come into the calculation?
Refrigerant type doesn't have a significant play in it. There's no refrigerant that's more energy efficient than others. There are refrigerants that are tied to specific chillers. Some of the more energy efficient, some of the more environmentally friendly refrigerants may result in slightly higher kW per ton. But the best way to do a very quick and dirty chilled water savings calculation is to use weather bin data. How many hours of the year the outside air operates at certain weather bins, and then take that IPLV, integrated part load value curve, and every chiller and every manufacturer can give you that. What is its kW per ton at 25%, 50%, 75%, and 100%? At a minimum, you can use those for the different weather bins. So kW per ton times hours, time your peak cooling load, or your cooling load at each of those bins, and you can come up with an estimate for kilowatt hours in each weather bin. Do kWh before, kWh after, and do a quick calculation of savings that way. The most accurate way is to do a building and energy simulation model using eQuest or Train Trace or something like that. But that's you can do it using just a spreadsheet with weather bin data and come up with a pretty good tool. Are there any more?
Oh, sorry, I was muted. We do have several more, but we're not going to be able to get to all of them, so I apologize. We will address a couple more, though.
Okay.
What are the big gotchas that seem good in design, but then end up not working?
That's a good question. So as I mentioned before, one of them is putting variable frequency drives on the cooling tower fans. Some people think that's a clever way to save energy, but it actually hurts the system as a whole when you're trying to drive that condenser water temperature down to save energy at the chiller. Let's see, what else is there? So obviously, first cost-driven decision making will cost you more in the long run. So someone may make a decision to get a chiller that won't have variable speed compressors because it saves a little money up front. So by making first cost decisions may hurt the long-term and life cycle costs and energy consumption of the system. So my recommendation is to always focus on life cycle costs when making decisions about the chilled water system.
Thank you. When is the best time to consider primary/secondary pumping system?
When you have a significantly variable load in the building, say
the cooling load of the building is not constant. It varies over the time of day. And what a primary secondary system is you have a primary loop that runs chilled water from the chillers to a heat exchanger and then back to the chillers. And then you have a secondary loop which uses a heat exchanger on the other side and then pumps chilled water to the building. Because the chillers have a minimum load, 20-25% load, and you can never go below that. If you expect the building to ever get to a point where it's at 10% load or 5% load, you would need a primary secondary system, because the primary loop can then operate at 20% load, but the secondary loop can provide the lower 10%, 5% cooling load with maybe the lower delta T's, because that water itself is not going through the chillers. So if you have a wide variation in cooling load, then I would recommend a primary secondary system.
Okay, thank you. There are still several more questions out there. Some of them are follow-ups to previous questions. So I will download the Q&A report and share that with you, Eric.
Great, yeah, I'd love to.
And then also in the follow-up email, you can see Eric's email address on the screen right now. So if your question was not answered, please feel free to reach out to Eric. And also I will provide that email address in the follow-up email that you will receive in the next 24 to 48 hours. I'm just going to take control back for a moment. First of all, I'd like to say a huge thank you to everybody for attending today, but an even bigger thank you to you, Mr. Oliver, for being here today, sharing your time and expertise with us for our members. Just a few quick reminders, as always, from AEE here. We do have AE East coming up in April, and we would love to see lots of you attending. So if you are interested, the web address is there on screen, and you may go there and find out the details and register. We do have other events in 2020. We have AEE West in Seattle, AEE World in Denver, and we do have our first event outside of the US, AEE Europe in Dublin, Ireland in October. We have lots of different certification options for you guys. We do have many online training options and live training programs up and running and scheduled for the year, so please check those out if you're interested in doing any more certification. And our next AE member webinar will take place in 3 weeks from today with Mr. Keith Waters from Schneider Electric, and he will be presenting supplying secure power with properly installed energy storage systems. So a huge thank you to everyone for being here today, and as I said, in particular to you, Mr. Eric Oliver. And on that note, goodbye, and I look forward to seeing you all again in 3 weeks.
Thank you very much.
Thanks. Bye.